Okay, sir, you can start now.
Hello everyone, good evening. I, Dr. Vinay Jain from Agilent Technology, welcomes you in this webinar on atomic spectroscopy. First of all, I would like to thank AOAC for organizing e-learning webinar series. So during this webinar, what we will discuss today, we will discuss about the spectroscopy. We'll also discuss about the historical background. During the day, we will also discuss about the atomic spectroscopy, different types of atomic spectroscopy called as the atomic absorption, atomic emissions. We will also discuss about different techniques like AAS, ICP OES, ICP MS. We'll also discuss about the selection of technique, how we'll have to select the technique for the quantification of the elements in food. We will also discuss about the steps for analytical workflow. We'll also discuss the most important one, do's and do nots, while we have to work into the lab for the quantification of elements. So first, what is spectroscopy? So spectroscopy is the study of interaction between matter and electromagnetic radiation. You can also call it the interaction between light and matter. When there is an interaction between light and atom, it is called as the atomic spectroscopy. For example, AAS. And when there is an interaction between light and molecule, it is called as the molecular spectroscopy. For example, UV. In next slides, we will study about atomic spectroscopy with respect to atomic absorption and atomic emission. But let's study the historical background. So what is the history talks about? How it is the origin of the spectroscopy? If we will go back to the history, in 1666, Sir Newton using a prism to separate the white light and became the first person to prove that white light was a mixture of many types of rays rather than a single entity. He observed that when a narrow beam of sunlight strikes the glass prism at an angle, some is reflected and some of the beam passes through the glass. If we can see here that some of the beam passes through the glass and emerging at different color bands. And he originated divide the spectrum into 6 named. So what are the 6 named? He called them as different colors: red, orange, yellow, green, blue, and violet. But later on he added indigo also. So these are the 7 colors of the light, which is basically the origin of the spectroscopy. So what is atomic spectroscopy? So today, basically, when we are talking about any elemental and metallic property to a quantification, so we have to understand what is atomic spectroscopy. Basically, atomic spectroscopy is based on the Bohr's model of orbital theory. And if we talk about the Bohr's model of orbital theory, when an electron or thermal energy are added to an electron, it takes up an additional energy and migrate from ground state to the excited state. But as nothing is stable in the excited state, so these excited electrons start emitting energy and fell back to the ground state. In doing so, electrons emit their excess energy. So they are, if you can see, they are emitting energy at different wavelengths. And this is called as the atom emit radiations. The resulting emissions, basically whatever the emissions lines they are emitting, they are characterized by their frequency and the wavelength. So what is measured, how it is measured, that is most important. So when we talk about the what is measured, so it is important that if we can see here, the nucleus consists of the electrons, protons also, but here if you can see the electrons, they are moving into the nucleus. So when they migrate to the higher energy level, so the absorption of energy causes an electron to move a high energy level. It is measured by using a technique called as the AAS. So the excited electron will eventually fall back to the ground states, and the emission of light from excited to ground state is measured by a technique called as the MPAS and ICP OES. That is the inductively coupled plasma optical emission spectrometry. But if there is enough energy, the electron will leave the atom completely and leave behind the positively charged ions. Then it is measured by using the technique called as the ICP MS. Basically, at this stage, the atoms convert into the ionization. ICP MS is nothing but the inductively coupled plasma mass spectrometry. So what is the principle of AAS? AS technique rely on the fact that an atomized element will absorb light of a characteristic wavelength, elevating it from ground state to the excited states. The amount of light energy absorbed is proportional to the number of analyte atoms in the light path. This technique is calibrated by introducing non-concentration of analyte atoms into the light path and plotting the absorption versus concentration curve. Basically, when we are calculating, when we are any techniques, and the atomic spectroscopy, when we are calculating our concentration of any analyte into our sample, so we have to use the NIST traceable certified reference material. And this AS is based on the principle of Lambert's-Beer law. So what is the relation between light absorption and analyte concentration is defined by using a fundamental law of light absorption, that is the Lambert's-Beer law. So what Lambert's talks about? So when talking about the Lambert's, is talking about the portion of light absorbed by a transparent medium is independent to the intensity of incident light, and each successive unit thickness of the medium absorbs an equal fraction of the light passes through it. And when we talk about the Beer's law talks about the light absorption is proportional to the number of absorbing atoms in the sample. If you can see here, this is the incident light, the transmitted light. So when it is passing through the sample, the amount of light something absorbed into the sample. So when we combine the Lambert's-Beer law, the absorbance is directly proportional to the concentration. Why? The reason being, if you can see the B and A both are the constant. A is the absorbance and the B is the length path. So if the length, because the length path of all the analyte, all call as the from the standard talking about your sample is remain constant while analyzing. So A and B remain the constant. So A is directly proportional to C. So since A and B are constant, so absorbance is directly proportional to concentration. So if we will see practically the Lambert's-Beer law, you will get the ideally you will get a curve like this, the absorbance versus concentration, you will get always a straight line. But actually, up to a certain after a certain level, it becomes saturate and your curve start moving like this. So it means we have to, if you will get a curve like this, it means you have to select the another wavelength. So this is the reason why when you are working on the AS, you will get a number of wavelengths, spectral lines you have to select when you are quantifying using the AES. What are the basic instrumentation of AS? So we are, the basic instrumentation consists of the hollow cathode lamp. So if you can see the hollow, this is the hollow cathode. First is the hollow cathode lamp. When talking about the hollow cathode lamp, basically what is the role of hollow cathode lamp? Hollow cathode lamp emits light for element of interest. That is why the hollow cathode lamp is also called as the source of light in atomic absorption spectroscopy. Then is the atomizer. The second part is the atomizer. This is, you can also call it as the sample introduction system, also common to the atomizer. What is the role of atomizer? So the atomizer converts liquid sample into free atoms which absorb energy from the lamp. When I'm talking about the lamp, it means here we are talking about the hollow cathode lamp or HCl lamp also. We can also call it the HCl lamp. So the atomizer converts liquid into the free atoms which absorb energy from the lamp. Then third is the monochromator, which the monochromator selects the wavelength used for the measurement of the analyte. The last is the detector, which measures the light absorbed by the free atom. This is how the lamps looks like. If you can see here, the cathode is made up of element of interest. And obviously, since each element is dedicated to analysis of a single element, although nowadays commercially few multi-element hollow cathode lamp is also available into the market, but talking about the AS, it is a sequential technique, and this is the biggest limitation of AS. You cannot do the multiple element by using the AS. So this is the basic concept. This is the limitation of the AS. You cannot do the multiple elements. Talking about the atomizer in the AS, the atomizers can, what is the role of the atomizer? Atomizers, the atom can absorb discrete amount of energy in the form of heat or light at different wavelengths. So an electron may change energy level, an atom can absorb or emit the energy. If you can see, the atom from the ground state is going to the excited state, and from the excited state to the ground state. So atom become excited, and excitation is explained by the transmission of an electron from the inner orbit to the outer orbit. So if you can see here, it is gaining the energy, and it is here it is losing the energy. It means here, if you can see the adding the energy, it means it is absorbing the energy, and here it is emitting the energy. So what is the process inside the atomization? Basically, atomization is the process that converts the liquid sample into the free atom. So basically, when we are preparing our sample by using the different sample preparation technique, we always get our analyte in the solution form. So when we are injecting this solution into the AAS, so it is converted into the aerosols, and from the aerosols, your samples went out into different steps, converted into the solid, liquid, melts, vaporization, and atomization. And when it come into the light, and when your atomized atoms come into the light beam, it is measured. Here, element, if you can go to the left side, element M undergoes different stages: the solution, nebulization, dissolution, vaporization, atomization, excitation, and the ionization. This is the process of atomization. So basically, in the AS, different types of atomizers are used. So the flame is one of the AS atomizer most commonly used. Other than the flame, the graphite furnace, you can also call it as the graphite thermal analyzer, and third one is the vapor generation analysis. So first we'll discuss about the flame AS atomizer. Basically, two different types of flames are used: air acetylene flame and the nitrous oxide flame. Talking about the air acetylene flame, you can reach the temperature up to 2300 degrees Kelvin, and whereas talking about the nitrous oxide, you can reach the temperature close to 2900 degrees Celsius. So the selection of the flame is very important when we are analyzing the elements. For example, if suppose we are looking for the element like calcium and in the food, so basically it's very difficult to rupture the bond at 2300 degrees Celsius in the air acetylene flame. This is the reason why when you quantify the element like calcium, or you have to use the nitrous oxide acetylene flame. Similarly, if you are working with the refractory elements like aluminum, then again you have to use the nitrous oxide acetylene flame. Otherwise, talking about the simple element like lead, cadmium, iron, copper, manganese, magnesium, sodium, potassium, all those elements you can easily do by using the air acetylene flame. So, but each technique, as I mentioned, that each technique has its limitation. When I'm talking about the flame AS, it has a very short precision. Talking about the precision, and it has a you can not run an AS for a long duration. If suppose you plot a linearity, and after plotting a linearity and you want to run the sample for 3 hours, 4 hours, then definitely you have to recalibrate your AS with the suitable certified reference material. AS also have the limitation in terms of the long-term talking about the linear dynamic range. It has a 3-order dynamic range. It means if suppose you are looking from the lower ppm level to the higher percentage level, 6 order or 7 order, you cannot do by using the AS. You can do only up to the 3 order of magnification. Talking about this is the advantage of flame AS, and these are the limitations. So talking about the limitations, AS is not a sensitive technique. If suppose you are looking for the elements in the lower PPT level or in the lower PPB level, then it is not possible to quantify by using the flame AS. Talking and the biggest limitation is that the use of the flammable gases. When we talk about the flammable gases, as I mentioned, there we are using the acetylene flame, which is a flammable gases. So unattended operation in the AS is not recommended anywhere. So this is the biggest called as the limitation of the AS. The second atomizer techniques with the AS is the graphite furnace. When I'm talking about the graphite furnace is, yes, it is a very sensitive technique, and sometimes in the graphite furnace you can also call it as the GTA, graphite thermal analyzer or graphite thermal atomizer. Sample is directly injected into the graphite tube and electrothermally heated in different stages to atomize the analytes. So basically, they are the different stages in the graphite. So when you insert your sample into the graphite tube, so first it dry your sample. So if you can see from here, from 0 to close to called as a 70, 60, 65 degree, drying your sample, removing all the solvents or removing all the mineral acids from your sample, then doing the ashing of your sample up to 400 degrees Celsius or close to 400 degrees Celsius, and after ashing it is doing the atomization. And where you can see here in the blue, temperature up to 2400 degree Kelvin Celsius. So it means it is a sensitive technique. You can do the element in the lower PPT level and PPB level also, but it has a large limitation in terms of the technique is very slow. It will take close to 1 hour to 2 hours to analyze a single elements, poor precision, only 2 order dynamic range, and more of chemical interferences are required. So you have to use the chemical suppressors, you have to use the different modifiers when you are working on the graphite furnace. Graphite furnace also has the limitation in terms of you cannot do all the elements by the graphite furnace. It is limited to close to 48 to 50 elements only you can do by using the graphite furnace. Graphite furnace is a complementary technique to conventional flame AS and added some advantage to the analysis in terms of the sensitivity. But the biggest advantage of the graphite furnace is you need only 20 microliter or 40 microliter of the sample for the estimation. For example, if suppose you are looking for the lead at the lower level and you have the AS with the GTA, so you can easily do the element like lead by using the GTA at the 1 ppb level also, which is not possible by using the flame. Talking about the next technique called as again in the AS is the hydride generation, vapor generation accessories. So here is the hydride generation techniques. So when we talk about the hydride generation technique, only the limited elements you can do which forms the volatile hydrides. So if you can see here, only the arsenic, tin, bismuth, antimony, tellurium, germanium, and selenium. These are the elements which you can do by using the vapor generation accessory. Here we have to use the reducing agent, which is nothing but the sodium borohydrides, which convert them into the different types of hydrides, volatile hydrides, and in the presence of hydrochloric acid. And those hydride vapors entering into the light path. Similarly, talking about the cold vapor technique, mercury is the only element which you can do by using this vapor generation accessories in the cold vapor, where you are not supposed to use the flame. So if you can see again the hydride generation technique and the cold vapor generation techniques, both have different advantages and the limitations, because talking about the cold vapor only it is applicable for the mercury, but talking about the precision, yes, good precision and good sensitivity. Similarly, if talk about the VGA, again the VGA has a good sensitivity and the good precision, and it is a faster technique as compared to the graphite furnace. But the limitation is it is applicable for only limited element. If suppose you want to estimate the element like lead and cadmium or talking about the copper and iron, it is not possible by using the graphite, by using the vapor generation accessories. So now if you can see the periodic table, those in the yellow color are possible by flame, and whereas in the orange color by flame and furnace. It means only by using the furnace we can do limited samples we can estimate, whereas other not possible by using the flame, or not possible by using the furnace. Again in the flame you have to select the techniques, either it is air acetylene flame or the nitrous oxide acetylene flame. Come to the another techniques, atomic spectroscopy technique called as the atomic emission spectroscopy, which overcomes few of the limitations of the AS. Like basically when we talk about the AS, it is a sequential techniques and you can do the sequential analysis. It means one after the another. So use of the hollow cathode lamp is also the limitation of the AS. So when we talk about the atomic emission techniques, this technique rely on the fact that once an atom is of a specific element is excited, it emits light in a characteristic pattern of wavelength as it returns to the ground state. And the technique used in AES is called as the ICP OES, inductively coupled plasma optical emission spectroscopy. So basically, what is plasma? First, we have to understand, here we are talking about the plasma. So plasma is nothing but the fourth state of matter, solid, liquid, gas, and the fourth state is called as the plasma. Plasma is the fourth state of matter consisting of highly ionized gas, which contains mainly electrons and ions. So basically, in the ICP OES, an argon inductively coupled plasma is generated, which has the temperature close to 10,000 degree Kelvin, which is used to dissolve it, atomize, and excite the atoms in the liquid sample and has been nebulized into it. The intensity of the light emitted is measured using optical detectors at the wavelength characteristics of the element of interest. No hollow cathode lamp is required in case of the ICP OES. These measurements can be compared to a standard to quantify the concentration of the elements with respect to the NIST traceable certified reference materials. So if you can see here, what are the advantages of ICP OES? It is a fast sample throughput technique. If suppose you are looking for the 73 elements, so in a single minute you can do all the 73 elements. It is simultaneously technique, not like the AS where you are every time you have to put the hollow cathode lamp. So it is a simultaneous multi-element analysis from sub ppb to higher per ppm level or higher percentage level. You can estimate in a single run. So talking about the ICP OES, it has a 6th order of linear dynamic range. It can tolerate complex matrices also. And here we are using the argon gas, which is nothing but an inert gas, or the noble gas come into the zero group, which is safe to use into the laboratories. It has a few limitations also. So if I will compare the ICP OES with the graphite furnace, it is not as sensitive as compared to the graphite furnace, but it is sensitive as compared to the AS flame. It is sensitive as compared to the AS VGA, that is a vapor generation, hydride generation. ICP OES has other limitation. You cannot do the isotopic analysis by using the ICP OES. You cannot do the speciation studies by using the ICP OES. So when talk about the basic instrumentation in ICP OES, it comprises of argon plasma, spectrometer, and quantification of the, obviously the software required for the quantification of your analyte. So in ICP OES, plasma torch can be viewed axially or radially, and sometime nowadays dual view ICP OES is also available into the market. So basically, what is the advantage? What is the significance of axial view and the radial view? If suppose you are looking for the high sensitivity, then axial view is one of the best called as a torch view in the ICP OES. But if suppose you want to handle the high TDS sample, then radial view is one of the best view in the ICP OES. Nowadays, dual view ICP OES is available into the market, which is working simultaneously in the axial view and the radial view, which can handle the high TDS sample up to say called as the 20-25% of the TDS, which is highly sensitive, working in the axial as well as radial view. So what are the key application of ICP OES in the food matrix? So it can monitor the trace level of elements like lead, cadmium, arsenic, and mercury in food and farm products. It is also used for the estimation of the micronutrients. If suppose you are looking for the micronutrients like sodium, potassium, all the alkali metals, talking about the alkaline metal like the calcium and magnesium, you are looking for the micronutrients like the copper, boron, magnesium, so iron, zinc. You can also estimate by using the ICP OES. Determination of essential element in water, you can also do. At the same time, if suppose you are looking for the fortified elements, that also it is possible by using the ICP OES. This is the view how the ICP OES looks like. Come to the next technique called as the ICP OES. Basically, is ICP-MS. ICP-MS is nothing but the inductively coupled plasma mass spectrometry. It is a highly sensitive technique, multi-element analysis technique. If you can see, the ICP is the inductively coupled plasma, where again the temperature of the plasma is close to 10,000 degree Kelvin. It uses the high temperature ion source. Basically, the ion source is nothing but the plasma, which decomposes, atomizes, and ionizes the sample, just like what we are doing, what we are discussed in the ICP OES. Once it ionizes your sample, so the mass spectrometer is the detector where quadrupole filter the mass based on mass to charge ratio. So ions are measured from lower PPT level to higher ppm level. ICP-MS has several advantages. If I will compare it with the AAS, ICP, OES, with different mode of atomizer, so ICP-MS has a high sensitivity, because here you can estimate the element into the lower PPT level. Talking about 5 PPT, 10 PPT, you can easily estimate by using ICP-MS. Highly matrix tolerance, irrespective of the matrix, all the matrix ICP-MS can tolerate. Large linear dynamic range, 10 order dynamic range of ICP-MS. So nowadays 10 order dynamic range, it means suppose you want to estimate elements in the, say you are looking for the heavy metal, you are looking for the micronutrient into the food, all the elements you can estimate into a single run, because here it is a 10 order dynamic range. Long-term precision, just like AS, we are discussing about the AS, where you, after every 2 hours you have to plot the linearity ones again and again. So here in this case, talking about the long-term precision, so once you calibrate the system, so after 6 hours, 8 hours, you will find the same precision in terms of percentage RSD, in terms of the bracketing of the standard. You can also do the speciation studies. I will discuss in the next slides about the speciations also. Organic solvent you can directly inject into the ICP-MS. Like, for example, suppose you have an edible oil. So you can dilute your edible oil into the suitable solvent and directly inject into the ICP-MS. High sample throughput, since you can estimate all the elements from lower level to the higher level and have the large linear dynamic range, it means you can estimate all the elements in a single minute. So the system is highly sample throughput. Talking about the process in ICP-MS. So in ICP-MS, basically liquid sample converted into aerosols, where fine aerosols enter into the plasma for atomization and followed by the ionization. So here is an example. When we are adding an energy to a, we have taken a small example of beryllium. When we are adding an energy to the beryllium atom, what's happened? Because we know that the number of proton is equal to number of electron. By adding an energy, that electron moves out from the outer orbit of this beryllium, and it converted into the beryllium ion in the plasma due to the high temperature of the plasma. Now you can see, because it one of the electrons removed, so it get a positive charge here. So basically what plasma does, plasma breaks the molecule and forms the atoms. And what will happen into the atoms? It removes the electron from the atom and ionizes them with and measures the amount of ions. So talking about in general about the ICP-MS, we have discussed about the ICP-MS, the argon ICP as a high efficient ion source. In the ICP-MS, mass spectrometer separates the ion based on their mass to charge ratio. Wide elemental coverage. Talking about the wide elemental coverage, it means all the stable elements on the earth you can do by using an ICP-MS. From lithium to uranium, almost all the elements you can do. Either it is alkali metal, alkaline metals, heavy metals, transition elements, rare earth metal, platinum group element, lanthanide series, actinide series, or either it is a non-metal. When I'm talking about the non-metal, which are not possible by using the AAS, you can also do the isotopics and the speciation study by using the ICP-MS. So when we talk about the instrumentation of the ICP-MS, it is a schematic layout of the ICP-MS. So first is called as the sample introduction system, which basically contains the nebulizer, spray chamber, and the peristaltic pump. What is the role of the sample introduction system? It converts the liquid into the aerosols. Nowadays, the sample introduction system, especially the spray chamber, is available in the in few of the ICP-MS, the Peltier cooled, where you can set the temperature from -5 to 20 degrees Celsius. Because in my earlier slide, I discussed that you can directly inject the organic solvent into the ICP-MS. So in that case, you can set the temperature of the spray chamber at -5 degrees Celsius, and you can directly inject the organic sample into the ICP-MS, like edible oil, either it is a groundnut, mustard oil, coconut oil, or talk about the alcoholic and the non-alcoholic drinks, you can directly inject into the ICP-MS. Now the second part is called as the plasma source or the ion sources, which contains of the HMI, that is the high matrix introduction system, ion lenses, different types of the ion lenses, and the role of this plasma ion sources and the ion lenses is to focus the ions and remove all the photons and neutrals, basically which are generated during the generating the plasma. Now your ions enter into the octapole reaction system. This is the ORS. So octapole reaction system, which removes your polyatomic interferences by using an inert gas. So here you can use the inert gas like helium. So by using the helium, you can remove all the polyatomic interferences, and it is based on the principle of kinetic energy discrimination. After now, up to this stage, you remove all your interferences, octapole reaction system. Now your analyte enter into the QMS, that is a quadrupole mass spectrometer, that is called as the quadrupole. So what is the role of QMS? It separates the ion based on the mass to charge ratio. So the separated ions enter into the detector, and detectors detects the ion and transfers the counts. Basically, when we talk about the detector, it is most of the time it is available in the market is the electron multiplier diodes. If you can see here is the electron multiplier diode detector, which works in two different modes simultaneously. One is the pulse mode, another is the analog mode. If suppose you want to quantify at the low concentration, then detector measures the pulse in the pulse mode, and if your concentration is high, then it measures into the analog mode. Simultaneously, we will, as an analyst or as a chemist, we are not supposed to select the mode, just the software automatically select the pulse and analog mode. So what's happened to the detector when the the charges which are ions which are coming from the quadrupole, those ion beams from the quadrupole is attracted to first diode, and the secondary electron, if you can see from here, the secondary electrons are released from the surface, and electron impact diode and produce the additional electron, and they start multiplying. So this is the reason why the detector, why the ICP-MS has a 10 order dynamic range, and it is highly sensitive techniques. You can also hyphenate the ICP-MS with the HPLC, and when you hyphenate the ICP-MS with the HPLC, it is called as the LC-ICP-MS. So what is the advantage? Why we are talking about the speciation here? So if suppose you want to estimate the trivalent arsenic or pentavalent arsenic, so ICP-MS will give you the total arsenic. Whereas if you hyphenate the HPLC with the ICP-MS, it will give you the trivalent arsenic, pentavalent arsenic, dimethyl arsenic acid, monomethyl arsenic acid. So which is the regulatory requirement as per the European norms in the rice. So you can easily estimate all those speciation study by using the LC-ICP-MS. Similarly, if suppose I will talk about the FSSI, you want to estimate the inorganic mercury, you want to distinguish in between the inorganic mercury and methyl mercury. So again, you need a HPLC along with the ICP-MS and form the LC-ICP-MS. Similarly, trivalent chromium, hexavalent chromium, ferrous, ferric. So you have to use the LC with the ICP-MS. But if suppose you are looking for the organotin compound, then you have to hyphenate the GC with the ICP-MS and forms the GC-ICP-MS. So this is the futuristic requirement and current requirement also, and the futuristic requirement also for the speciation studies. So talking about the selection of techniques, which element we have to select, it is most important that which element we want, that which technique we have to select for the estimation of our analytes. So first and foremost is the element, selection of the element. What is the regulatory requirement? What is your scope of work? Which element you want to do? It depends upon the detection limit. When I'm talking about the detection limit, what is it means? What is the regulatory requirement for which you are working? So for according to which you want to detect your elements, how many samples you have, and what is the how much sample quantity. If suppose, for example, you have a very small quantity of sample, say if suppose you have only 5 ml of the sample and you want to estimate element like 25 to 30 element, it is not possible by AS. So in that case, you have you have to select the technique like ICP MS. In general, if suppose you have large number of samples, many elements, you have to select the technique like ICP OES, ICP MS. If you have only few elements, then flame AS and graphite furnace is one of the best technique. But at the same time, if you have only few elements, you are looking for the load detection limit, then we cannot select the like the flame AS, then only we have the option like the graphite furnace along with the ICP MS and ICP MS. So this is one of the most important step of how we have to select the technique, how we have to choose the technique when we are carrying out our elemental study in the food products. So what is analytical workflow? So first, what we have to do when we are preparing our sample, first we have to homogenize the sample. It's always important that if we want to get a congruent result, our sample should be homogenized. So adequate amount of sample representing the complete load is one of the best requirement for the homogenization. Then we have to digest the sample. When I'm talking about the digestion of the sample, so there are different types of digestion techniques are available. Some few of the regulatory, they are talking about the ashing, few are talking about the Geldar method, and nowadays microwave digestion technique is also available in the market. So when we talk about the microwave digestion technique or any digestion technique, so the main purpose is that the complete decomposition of matrix. So when we are digesting the sample, the purpose is because talking about, if suppose I will take a small example, suppose I will take a fruit, and in the fruit I want to estimate the element. So my interest is the inorganic part of that fruit. I'm not interested in the organic part. So what we will do, we will digest them. We will decompose the organic matrix by using the suitable mineral acids. So what are those mineral acids? Those mineral acids are nitric acid, hydrochloric acids, might be hydrogen peroxide, and sometimes might be the hydrofluoric acids. So by using the digestion technique, we will do the complete decomposition of the matrix. It is most important that prevent loss of analyte due to volatility. We have to use the ultra pure grade acids. So the reason being why I'm talking about the use ultra pure grade acids, it means so that when you are running your method blank or reagent blank, so you will not get a high value. It is most important that we have to carry out the reagent blank and spiked sample simultaneously when we are preparing our sample. So irrespective of the technique, either you want to estimate by AAS or ICP OES or ICP MS, every time we have to prepare the blank along with the spiked sample. So ensure that we have to ensure that our complete elements remain into the solution, and we have to do the recovery and precision studies. Once the digestion is complete, we have to make up our solution. That's why I put the step called as a concentration, so that as per the desired detection limit and maximum permissible limit, we have to dilute our sample. For example, suppose we have taken 0.25 gram of the sample, that how much quantity, how much volume we have to make it. Either we have to make it 20 ml, 25 ml, 50 ml, or the 100 ml. This is about the concentration. So once we concentrate, now our next step is the Q and Q determination, that is qualitative and quantification determination. So what actually we are looking for? Nowadays, few of the instruments are available into the market, which are doing the qualitative information along with the quantification determination. For example, if suppose you are quantifying 4 elements, but at the same time, few of the instruments are available which can quantify all the elements simultaneously. So when you are doing the qualitative and quantitative determination, selection of suitable analytical technique is one of the most important factor. You have to use the well-developed and validated analytical method, and always use the niche traceable CRMs, because at the end of the day, when you are preparing your submitting your results, you have to calculate the measurement of uncertainty. Talking about the validation of results, so you have to plot the linearity. Obviously, talking about the R value or the correlation coefficient, it should be more than 0.99. You have to carry out the precision, intraday precision and intraday precision with respect to the percentage RSD. Accuracy at different level, limit of detection and limit of quantification, ruggedness and robustness. So that once you have developed the method, once you've done the analysis, when it will go to the another lab, that chemist will also get the same result. So what we have discussed in the analytical workflow, we discuss about the homogenization, then we discuss about the digestion, we discuss about the method development and validation, selection of technology, and last about the data interpretation. Now talking about any techniques, now the techniques they come up with the software where you can directly interpret the data. So you have to interpret the data as per the regulatory requirement, so that you can not only estimate the elemental impurities or heavy metal contaminations, but at the same time you can also do the functional food, nutraceutical in the nutraceuticals, fortified food also, micronutrients also, as per the regulatory requirement or as per your scope of work. So talking about the next slides, here we are talking about the do's and do nots while working into the lab. It is most important, because you select the technique, you perform the analysis, everything you have done. But what we have to do, what precautions we have to take when we work into the lab. So first and foremost important is the lab, our lab should be clean and control temperature with and humidity. Otherwise, what will happen if your lab is not clean? There is a possibility that you will get a contamination from the environment. Similarly, the next step is about the lab wares should be cleaned and calibrated. Always, I will prefer that use the class A calibrated lab wares. Your volumetric flask, your pipettes, your micro pipettes, your measuring cylinder, everything should be calibrated. And in fact, your analytical balance should be calibrated. We have to understand the scope of work, what is our requirement, what we want to do, perform the analysis, use the PPE, that is the personal protective equipments like lab coats, like gloves we have to wear when we work into the lab. We have to awareness about the MSDS, that is the material safety data sheets, about the acids, which acids we are using, the chemicals, different types of chemicals, the gases. We must have the aware about the MSDS of all these chemicals and reagents, gases used into the lab. Always use supra pure acids and gases. Always use the calibrated lab wares. In fact, the gas flow meter, mass flow controller should be calibrated. We have the proper exhaust system, so that because we in the talking about the atomic spectroscopy, always we are using the mineral acids. We are using the nitric acid, we are using the hydrochloric or the sulfuric acid. So when we are preparing our sample, there is a possibility you will get a fumes into the lab. So always recommend that you have to use the proper exhaust system. So always keep the reagent at designated places, so that once we complete the analysis next day, suppose we want to use the same reagent, we'll get at the place. Always use the NIST traceable certified reference material and follow the good laboratory practices. And I will not talk about more about the do nots, but it's most important that we never eat drink or smoke into the lab, and do not keep the organic solvents near to hot zone. Basically, most of the time we are in elemental spectroscopy. We are using the hot plates, we are using the muffle furnace, we are using the hot air oven. So we always recommend that please do not keep the organic solvents near to the hot zone. Otherwise, there is a possibility of some damage. Do not handle broken glassware without safety measures. It's most important, because while we are working into the lab, there is a possibility that sometimes our lab glasswares got broken. So we have to follow the proper safety measures when we are handling those broken glasswares. And do not keep acids and reagent bottle open after use. The reason being, if suppose there is a possibility that those acids and reagent will get contaminated. So this is all from my side. Thank you very much. And these are my this is my email ID and mobile number. You can write to me any questions, any queries. I will be happy to provide you the solution. Thank you very much.